Hello, it's Stat 134, Lecture 29. You have Quiz 6 on Wednesday covering sections 4.6, 5.1, and 5.2. No surprises there. Last time we discussed the beta distribution, section 4.6. So here R and S are any positive real numbers, and P is beta RS if it has density given by the formula shown here. Please note that the variable part here is p r to the minus 1, 1 minus p s minus 1. So, and here p is between 0 and 1. There's no accident that I write p because p is a probability. So we're going to see some applications for beta now. So one is that it's a generalization of uniform ordered statistics. So if you throw n darts at the unit interval, the kth order statistic is beta k n minus k plus 1. That's what we saw last time. And so in particular, we can see that when n is 1 and k is 1, that means that you're just throwing one dart. And so in that case, the first ordered statistic is just the standard uniform, and that is beta 1, 1. So another application, actually the most common application is thinking that beta RS represents a distribution of probabilities. So here enters Bayesian statistics. So probabilities or parameters for distributions aren't fixed constants, but rather they have distributions. So for example, the p in a binomial isn't just a fixed constant, but rather it is something that has a distribution, and that distribution can change depending on data that and so you start with some prior belief of what that distribution is. You have a likelihood, which gives you basically like a binomial formula, something that gives you a rule for how what the probability of getting different values of your random variable. And then you have a posterior, which is basically an updated probability distribution given results from an experiment. So we saw in lecture 2, right at the beginning of the course, that posterior is proportional to likelihood times prior. So here I've sort of written down this in sort of density notation. And so commonly your prior will just be the uniform distribution, which has density 1. And your let's say your binomial, your likelihood could be, for example, the binomial formula or the geometric formula or the negative binomial formula. All of those would then lead to a posterior, which would be a beta distribution. So I've sort of fleshed that out for you here in an example. So let's say that you have a probability p coin, where p is unknown. You flip the coin n times and you get x heads, right? So question, what is the posterior distribution of p? Well, so we could make the prior a beta distribution, beta RS. So for example, if you didn't want any bias or subjectivity to what your prior is, you could make it beta 1, 1, which is the standard uniform. But notice that the prior has the variable part is pr to the minus 1, 1 minus ps minus 1. Now the likelihood would be binomial here. So, and the variable part of that also has this same form, in this case p to the x, 1 minus p to the n minus x. And the posterior then would be the product of these two variable parts, and that then the p's and the 1 minus p's you can look at what their powers are, And you see then that the posterior is going to be a beta, in this case x plus r and n minus x plus s. So the cool thing is that this posterior now you could let be a new prior if you were, let's say, to at a later time collect more data that would refine your distribution of p, giving you again a new posterior, and then it can go around and around in a cycle. So this is mainly how betas are commonly used in statistics. So we say that beta and the binomial are belong to the same conjugate family, just meaning that they're compatible. They're compatible in this way. The likelihood binomial fits nicely with a prior, which is beta, to give you a posterior, which is beta. We also talked about independent random variables last time. So the joint density factors into marginal densities. So today we'll just review some student explanations from the concept test from last time, and then we'll spend most of our time looking at examples of independence, marginal density, expectation, and then we'll just very briefly get started on independent normal variables and do that next time. So last time we saw this concept test. You throw down 8 darts. The variable part of the joint density of x is the third uniform ordered, y is the 6th uniform ordered statistic, and then we can see that the variable part of the joint density is choice B here, with x and y between 0 and 1, x less than y. So you necessarily have one dart going in dx and one dart going in dy. That leaves, so for x to be in u3, that means that 2 darts are going before x, and for y to be in u6 means that 2 darts go between 1 and y, because you have a total of 8 darts, and then that leaves 2 darts to go between y and x. So students wrote this explanation well, and I just show 2 samples of their explanations here. So then there was a follow-up question, and you're asked to whether this particular joint density, whether this function is a joint density. In other words, it integrates to 1, and you say yes because you recognize that x is uniform order statistic 1, and y is standard uniform order 6, and so on. So you can then ask whether x and y are independent, and to do this we need to find marginal densities. So remember what a marginal density is. So here I've just shown a picture for the discrete case. So for example, marginal y means that you fix a y and you add up the probabilities in that row. So you can see that in the formula here for marginal probability for y. P of y is the sum over all x in x for px comma y. So, and similarly for the marginal of x, you would fix x and then sum up all the cells above that x. So it works the same way for the continuous case. So for the example that we just did, we recognize this is a density, and here the marginal density, basically we fix in x and then we sum up all the probabilities for different y's, and in this case the what we're integrating over here isn't just the entire plane, it's actually just this triangle that's shown here. So we get an upper triangle here because x is less than y, and x and y are between 0 and 1. So you just get this little triangle here. So for example, to get the marginal for x, you would fix x, and then you would integrate your density fxy for y's between x and 1. So just look at the vertical line in red here that I've drawn. You're integrating from y is x to y is 1. And you can similarly do this to find the marginal density for y. And in that case, you pick your y, and then you're integrating from x is 0 to x is y. And you can see once you find these marginals that we do not have independence because we don't get a factorization of the joint density. So expectation has the expected formula here where you need to you use the joint density, and we can just check this formula for the special case where g of xy is just y itself, and you will see that you get what you need to get because you know that y itself is actually uniform ordered statistic, sixth order statistic. So, and that's a beta 6,1. So the expectation of y we know is 6 over 6 plus 1, which is exactly what you get just doing it as a marginal, just using the definition, of expectation. So we did another example. So S and T are IID exponentials. X is the min of ST, Y is the max of ST. We want to find the joint density of X and Y. Are X and Y independent? So to find the joint density, notice that for X to be in dx and Y to be in dy, that's completely equivalent to having one of two mutually exclusive situations. Either ds comes before dt or dt comes before ds. So for x to be in dx and y to be in dy, we either have s in ds and t in dt with ds coming before dt, or we have t in dt and s in ds with dt coming before ds. So using the addition rule, you can write that out, what those probabilities are, just as I've done here. You see that the two probabilities on the right are completely equivalent, so we just get twice the probability that s is in ds and t is in dt. We can write out what these probabilities are in terms of the joint densities. The joint density, since s and t are independent, we get this factorization, and hence we get the formula shown here for the joint density of x and y. And so then as a concept test, you explored what the marginals are, and you can find the marginals either by integrate. So in the case finding the marginal density of x, you can integrate out y, or you can just say, hey, you know what, x is the min of s and t, so I know that, and since s and t are exponential, this works well using a CDF method, and I'll just write out explicitly what the probability of x greater than little x is, and then that'll give me what the CDF is, and I can just take the derivative of that to give me the density. So you did that, and similarly, the follow-up question was to find the marginal density of y. Same approach works. And then you can see that no, x and y are dependent because we don't have factorization. And finally, we ended just previewing a little bit of what we're going to do next time, which is independent normal variables.